Hello aspirants, welcome back to SKD's Note. So today we are going to discuss about electrical machines for assistant electrical inspector and other various examinations. In that we are going to study about effect of magnetic leakage flux on the operation of transformer. Okay, so how this magnetic leakage flux in the transformer is going to affect on the operation. Okay, so here this magnetic leakage flux is the part of the load component of flux which links either HV winding or LV winding, but not both. Understood? So it is not having any role in transferring power from one circuit to another circuit. Okay, so leakage flux, what it says, leakage flux is not having any role, okay, in power transferring from one circuit to another circuit. Okay, so while observing all the consequences, so what this magnetic flux or magnetic leakage flux will do, whether it is useful flux or not useful, how the behavior of flux, whether it is affecting the main flux or not, and we are going to discuss about the phasor diagram of this magnetic leakage flux on the working of transformer. Okay, so this is one, and another thing what we discussed, it links either of the winding but not both, either of the winding, not both. Okay, so this leakage flux, as it reduces power transfer capability will increase. Understood? More the magnetic leakage flux, lesser will be the power transfer capability. Lesser will be the leakage flux, more will be the power transfer capability. This you should understand. So magnetic leakage flux at primary and secondary increases with the increase in the load current, but it is independent of this applied voltage. Understood? So magnetic fluxes are available at primary and secondary are in phase with the respective current. Okay, here it is I1 consider, or I1 dash, here it is I2, likewise. Understood? Whenever leakage flux is considered at primary or secondary, some additional EMFs will be induced, okay, at the primary and secondary. Okay, considering them as EX1 and EX2 for primary and secondary respectively. So which lag behind the respective currents by exactly 90 degree. EX1 and EX2 lags behind 90 degree with respect to currents that we were going to see in phasor diagram while drawing the phasor diagram. Understood? So what are all the things you should remember while considering magnetic leakage flux on the working transformer? Correct? One thing, magnetic leakage flux is produced by part of the load component of the flux, okay, which is circulating in air. Here I have shown here. So it links either of the winding but not both, either it should be linking in HV or LV or primary or secondary. And one more thing we have discussed, so as leakage flux increases, the power transfer capability is going to decrease. As leakage flux is going to decrease, the power transfer capability gonna increase. And one more, so leakage flux nowhere related with the power transfer in the circuit from one circuit to another circuit. Always remember that leakage fluxes are in phase with the respective currents, okay, always in phase. So now we are going to discuss about phasor diagram of transformer under load with respect to magnetic leakage flux. Vector diagram or phasor diagram, okay. Transformer under load with respect to magnetic leakage flux, okay. This is what we are studying. Okay, so as usual we are going to take this flux, main field flux, as a reference. Here it will be magnetizing component of no load current, okay. So here it will be IW. What is this current? Reactive component or active, this is active component of current. So here it will be minus E1, correct. So then we have a resultant as I0, correct. This is I0. So then we will be having a current which is due to what? Load component of current, that is I1 dash in the primary side. This will be K, transformation ratio. The K will be always less than 1, okay. So the resultant of I1 dash and I0 will give you I1 vector, the total current. So here, as just now we have discussed that due to the leakage flux there will be a leakage current, right. That leakage current will be in phase. So here this is I1 dash, the secondary winding current will be exactly opposite to this one. So we are going to draw an I2 here. Here this angle will be what? This angle will be phi naught. So here in order to satisfy the Lenz's law, there will be EMF voltages with respect to applied voltage, where the secondary EMF magnitude will be lesser than primary one, correct. So again what we are doing here, EX1, that is leakage flux in the secondary winding, which will be 90 degree lags behind the respective current. Secondary side it will be what? Here it will be I1 dash, sorry, for this one is primary, EX1 is for primary, correct, I1. Then here I2 lags exactly 90 degree with respect to I2. This will be what? EX2, 90 degree here, exactly 90 degree. So now we are considering V2, okay. So in order to nullify this leakage induced EMF due to the leakage flux, we are introducing imaginary what? Imaginary inductances, okay, that we are going to consider now. So here V2, there will be an inductive drop for I2, okay. This will be I2 times X2, or Jx2. Likewise here with respect to primary side, in order to nullify the leakage EMF due to primary side, that is Ex1, we are going to introduce an imaginary inductance, that is Ji1 x1 drop. Okay, this will result in nullifying these Ex1 and Ex2 to get a good transfer capability. That will be around 2%, right? Correct. So in previous we have discussed, so this angle will be phi 2 here. So here you can see the leakage flux due to phi and phi 1 dash. Here phi is the main flux and this phi 1 dash will be load component of flux in the primary. So this will be a primary leakage flux. It will be 2% in the primary side. In the secondary side leakage flux, we are going to consider it is 2%. This is secondary leakage flux due to only phi 2. Understood? So we have drawn the vector diagram right now. Correct? So what else we left with? I think we left with nothing. So in order to compensate additional EMF, correct, Ex1 and Ex2, which are exactly lagging behind the 90 degree with the respective currents. In secondary it is lagging behind I2 90 degree. In primary it is lagging behind I1 here 90 degree. Correct? So now some imaginary inductive reactances we are all assumed, right, in series with the respective windings in such a way that the magnetic of drop across reactance is equal to the EMF in the winding due to leakage flux. Okay, as I said. So on primary side we are going to consider about that the leakage flux is equals to the imaginary inductive reactances. Correct? This will be in the primary side. Here x1, if you take, it will be Ex1 divided by I1, magnitude of Ex1 divided by I1. What is x1 here? X1 will be the leakage reactance of primary winding. Similarly, okay, leakage flux, leakage reactance. Understood? Of primary winding. Similarly, on secondary side, the same way, the imaginary inductive reactances will be equals to the induced EMF, that is due to leakage flux I2 x2, magnitude of I2 x2 will be equals to leakage induced EMF due to leakage flux in the secondary side. That will be x2 is equals to Ex2 divided by I2, magnitude of Ex2 divided by I2. So x2 will be here leakage reactance of secondary winding. Okay. So if you draw the equivalent circuit here, so we are introducing what here? In series and inductive reactance, right? Here it will be x1, correct? So here in the secondary side it will be x2. So here it will be I1, E1 due to leakage flux it will be Ex1, in the secondary side it is EX2. Okay. So from that equivalent circuit which we have drawn right now, so from the equivalent circuit, if we consider in the primary side, by applying KVL, V1 vector equals to minus E1. Why this minus E1 here? Lenz's law, to satisfy the Lenz's law. So this inductance drop which we have considered at the primary into I1 R1, this is winding resistance, okay, drop with resistance drop. So then we have minus E1 plus I1 vector. If you take common, we are left with R1 plus JX1. So then we have V1 vector equals to minus E1 vector plus I1 Z1. This R plus X JX will be considering as an impedance. Okay. So here Z1 is the leakage impedance in the primary winding. Okay. Leakage impedance of primary winding. Okay, because it is a function of leakage reactance. So here if you consider in the secondary side, E2 vector equals to V2 plus I2 R2, considering the resistance drop in the secondary winding as well. So plus then we have J times I2 X2. Okay. So what is this I2 X2? This is a reactance, inductive reactance drop at the secondary side. Here also we are considering with resistance drop. Okay. So then we will be left with V2 vector, taking I2 common here as well, R2 plus JX2. So then it will be E2 equals to V2 plus I2 Z2. Okay, here Z2 will be the leakage impedance of secondary. Correct. The impedances in the transformer is called as leakage impedance because it contains leakage reactance of the transformer, that is X, inductance, inductive reactance. So the condition that must be satisfied while transferring leakage reactances from either of the side, or from primary side to secondary side or secondary side to primary side or other sides, the PU reactance drop, the per unit drop, reactance drop should be maintained constant. The PU reactance drop before transfer is equals to reactance drop after. Okay, so let me write here. So while transferring leakage reactance from one side to other side, the PU, that is per unit drop should be maintained constant. Okay, this you should remember. So here the per unit reactance drop before transfer will be equals to reactance drop after transfer. Okay, remember this, the per unit reactance drop before the transfer will be equals to per unit reactance drop after transfer. So now we will consider transfer of reactance from secondary to primary. Okay, case 1. The second case will be the transfer of reactance from primary to secondary. So here it will be x1 will be as it is, we are referring the secondary towards primary, so it will be x2 dash. Here this is primary winding and it will be a secondary winding. This will be the equivalent circuit with respect to primary side. Okay, here the current will be what? I1, correct? So from this we are going to write that I2 x2 divided by E2. Okay, there will be a secondary current, this will be a secondary reactance, and this is what? EMF in the secondary side. So it will be I1 x2 dash divided by E1. So I2 x2 divided by E2 will be equals to I1 x2 dash divided by E1, this one. Okay, so then we will be getting x2 dash equals to x2 into I2 divided by I1 into E1 divided by E2. Okay, so from this we can write that x2 dash will be x2 divided by k square. Understood? So in the second case, transfer of reactance from primary to secondary, what we will get? So let me draw the equivalent circuit first. Correct, this is primary side and here it will be secondary side. So x2 is as it is and we are taking x1 out from primary towards secondary. This will be considered as x1 dash. Here from the above equivalent circuit, so here I1 x1 divided by E1 will be equals to I2, here it will be a secondary current, right? I2 x1 dash divided by E2. So here x1 dash will be x1 into I1 divided by I2. In previous case it was I2 divided by I1. Okay, so x1 into I1 into I2 divided by E2 divided by E1, you will get k square x1. Okay, so similarly total leakage reactance with respect to primary side will be considered as x01 x1 plus x2 dash, correct, which will be equals to x1 plus x2 dash. In last slide we have discussed that it will be x2 divided by k square. Okay, the previous in previous case we have discussed that due to winding resistance what going to affect on the working of transformer. There we are considering the resistance in series with the primary winding and secondary winding. Here we are just discussing inductive reactance in series with the primary winding and secondary winding due to this magnetic leakage flux. That's it. So the total leakage reactance with respect to secondary side will be what? So x02 will be x2 plus x1 dash. Okay, so which will be equals to x2 plus k square x1. If we consider the percentage reactance of transformer with respect to primary, we will get percentage of reactance equals to I1 x01, correct, x01 is this one and x2 will be this one, x02, divided by E1 into 100. Percentage reactance of transformer with respect to secondary will be percentage of x equals to I2 x02, correct, this is x02, divided by E2 into 100. So therefore the percentage reactance of transformer with respect to primary will be equals to the percentage reactance of the transformer with respect to secondary. Okay, so percentage reactance of primary will be equals to the percentage reactance of secondary of transformer. Okay, understood. As percentage reactances on both the sides, primary and secondary, are same, so these can be easily transferred from one circuit to one side to another side, that is primary to secondary or secondary to primary. When compared to reactance in ohmic value, hence the transformer leakage reactance are generally expressed in PU only, per unit values only. Okay, so now we are going to see the equivalent circuit, that is exact equivalent circuit of a transformer. So equivalent circuit of a transformer, okay, that is exact equivalent circuit. So transformer, working of transformer with winding resistance R1 with leakage reactance X1, there will be a current due to no load component of current. So there will be a two currents, active component and reactive component respectively, IW and I mu. This will be a resistance and this will be an inductance. Okay, R naught X naught, this we have discussed in previous class how it has come. This is in the primary side. Then we are going to, this is primary winding, this there will be a I1 dash. What is this I1 dash? This is the current due to load component of primary current. Okay, here it will be I1 vector, that's it. So then we have this is N1 raised to N2. In the secondary side, if we consider, what we will get, this is primary EMF, this is secondary EMF. I2 is I1 dash. Okay, so here we are getting secondary winding resistance R2. Here this will be a leakage inductive reactance X2 in the secondary side. You will get secondary voltage V2. Here you will get primary voltage V1. Correct. So then there will be a load impedance ZL. Okay, there will be a current I2 here. Understood? So this is the exact equivalent circuit of transformer. Now we are going to discuss that exact equivalent circuit of transformer when referred to primary, and then in second case we are going to discuss about how the exact equivalent circuit when referred to secondary. So this is very important. Okay, understand this. So now we are going to discuss what exact equivalent circuit of transformer when referred to primary. So here what we will get? We will get everything similar in the primary side, there won't be any change. So here this will be I0, these are active and reactive component of currents, that is IW and I mu. This is R0 and here it is X0, R1, X1. Here it will be an applied voltage V1 or source voltage. Correct. So here it will be an induced EMF E1. So we are referring to primary. So we are taking secondary components or elements into the primary side. Okay. So here it will be resistance and similar an inductance, that is reactance. So R2 dash will be R2 divided by K square. Okay. This we have seen that the second case, right, that is working of transformer with winding resistance. There we got this expression. Recently we have seen due to magnetic leakage flux how the transformer going to work. So we got this expression. So X2 dash will be X2 divided by K square. So here I1 dash equals to K times I2. This K is always less than 1. So here V2 dash will be V2 divided by K. So impedance, load impedance, that is ZL equals to Z1 divided by K square when the exact equivalent circuit is considered with or referred to primary. Next case we are going to discuss about exact equivalent circuit of transformer when referred to secondary. Okay. So we are taking all the primary side components into the secondary side, that's it. So here resistance, inductance, then we have I0, here it will be I0 by K, here I1 by K. This is K times V1. A resistive component here inductive component. So what we will get here, R0 dash will be K square R naught. Here X naught dash will be K square X naught. So we are taking all the primary components towards secondary component. Here resistance will be R1 dash equals to K square R1, whereas for inductive reactance this will be X1 dash equals to K square X1, correct? So here it will be an secondary current I2 will be I1 dash by K, okay. So here it will be an induced EMF due to primary side, it will be K times E1 is equals to secondary side EMF. Then we will get R2 winding resistance due to secondary winding and inductive reactance in the secondary winding, okay. So at last we will get load impedance and secondary voltage. This is the exact equivalent circuit of transformer when referred to secondary side. So first approximation to equivalent circuit is with respect to primary side. So place the shunt branch before the primary impedance. Understood? So then what we are going to discuss? So first approximation to equivalent circuit with respect to primary side, place the shunt branch before the primary impedance. That's it. So how it will become now? We are placing this shunt branch here first. So it will be, so let me draw in next slide, okay. Place shunt branch before primary components. What are those? Resistance and inductive components. Then it will be here I1, this is I0, no load current, no load component current. So you have active and reactive components current, IW and I mu. There will be an R0 and here it will be an X0, correct? So here it will be in the primary side, you will get a voltage V1. The total equivalent circuit placing the shunt branch before the primary component, that means merging all primary winding resistance and inductive reactance and secondary winding resistance and secondary inductive reactance, we will get R01 here X01. So the current will be I1 dash equals to K times I2. Here it will be a V2 dash in the secondary side. Then you will get here load impedance ZL dash, okay. So equivalent circuits of transformer, this is the first approximation, okay. This diagram says the first approximation of or with respect to primary. So here what are all the changes which we have made in the first approximation with respect to primary winding? So no load primary impedance drop is neglected, that is I0 Z1 neglected, okay. I0 Z1 is neglected. Similarly no load primary copper losses also neglected, that is I0 square R1 neglected. So leakage flux at the primary under no load condition is also neglected, since we are considering the load. So here V1, magnitude of V1 will be greater than induced EMF magnitude. Therefore I naught is overestimated here. That means what happens, I mu and IW are also more than actual value, more than actual value. Understood? So then iron losses are overestimated, but copper losses are underestimated. Iron loss are overestimated, copper loss, that is PCU, copper loss less estimated. All these deviations produce little error, since I naught is 5% of full load current. Okay. So here I naught is 5% of full load current. So now if we see the second approximation equivalent circuit with respect to primary side, in the second approximation equivalent circuit, the shunt branches is completely removed. In first case we are shifting the shunt branches first after the excitation. Later we are considering the winding resistance and inductive reactances. In second approximation, what we are going to discuss? Second approximation equivalent circuit with respect to primary. Okay. So here we are completely removing the shunt branch. The shunt branch is completely removed. Because I naught is 5%. Why? Because 5% of I naught is 5% of full load current, and it can be neglected. So the circuit will be R01, X01, there will be a ZL dash, that is load impedance, and here it will be V2 dash, correct? Here it will be V1, I2 will be I1 dash. Understood? So this is about the exact equivalent circuit of and equivalent circuits of transformers, on the working, how these are going to affect on the working of transformer. First case we have considered with respect to losses, then we are considered with respect to the iron, winding resistance, then we have seen the working of transformers and effect of working on transformer due to magnetic leakage flux. Okay, there will be a small leakage flux in either of the winding, but not both. Understood? That will be a 2% that we are considering. So in order to equate that induced EMF due to the leakage flux, we are going to introduce in series with the inductive reactances, that is in the primary and secondary side. So in the next class we are going to discuss about the losses in the transformers, or else in the next session I will be taking DC machines, that is DC generator and motor, so that we should finish the classes or topics early, because we are left with only 1 month for the assistant electrical inspector examinations. So I will cover one topic from the each machine concept. Okay, so 2 lectures video I will be posting DC machines respectively, then I will be posting DC motor, then synchronous machines, induction machines, then again transformers, so that we can cover all the subjects in lesser time. Okay, thanks for the watching video. If you like this video, please subscribe to the channel and share with your friends. Thank you.